Hey folks, we're going to talk about conditional probability a little bit more today. This is going to get glued in on page 18 of your notebook. These are your notes from yesterday. I just want to go over them and then help us finish them. So we talked about conditional probability of an event B in relation to an event A, and what that basically means is the probability that B is going to occur given the knowledge that A has already happened a particular way. And sometimes that changes the probability of your event if you're given partial information. So the example given is, let's say you toss 2 pennies. Your results can either be the first one heads, second one heads, first one heads, second one tails, tails heads, or tails tails. If the first penny shows heads and the other penny rolls under the table, you can automatically get rid of anything that started with a tails on the first flip. So the probability of getting both heads is no longer 1 out of 4. It's now 1 out of 2. So having partial information changes your probability, and that affected probability is called the conditional probability. The way that you write it looks like this, and the way that you read it is the probability of event B given A. So event B given that A has happened a particular way. If events A and B are independent, meaning one event does not affect the probability of the other event, then what ends up happening is the conditional probability of event B given A is simply the probability of event B happening, because remember, A has no effect on what happens in B. So the probability of B given A is just the probability of B. An example of that is, let's say we have 2 colored dice, one blue, one yellow, and they're rolled. What's the probability of rolling boxcars 2 6s? So a blue 6 and a yellow 6. Well, the probability of rolling a 6 on the blue die is 1/6, and a probability of rolling a yellow 6 is 1/6. So if I multiply that together, I get 1 out of 36. But then I ask, what's the probability of rolling boxcars knowing that the first toss is a 6? So because these are independent events, rolling something on one die doesn't change the probability of rolling on the second die. Since that's the case, then the probability of rolling a blue 6, given that you already rolled a yellow 6, is just the probability that you roll a blue 6, and that probability is slightly different than the one before because you have partial information. So that's why conditional probability sometimes changes your overall probability. So some classes were able to go on and some classes were not, so I went ahead and picked the key that didn't have anything from the inside. So the probability changes when you have partial information about that situation. If events A and B are dependent, meaning the probability of one event affects the probability of the other event, then we see that the probability of both events occurred is defined by a particular formula. The probability of A with the intersection of B, and if your class didn't go over that, we'll go over that in a moment. So the probability of A and B happening is the probability of A happening, equals, sorry about that, times the probability of B happening given the information about A. So the 2 probabilities happening, A and B, it's just that the probability of B has some information about it that we don't already know. Now, if your class period has not gone over this yet, if you will draw a Venn diagram somewhere on your paper. So here's your Venn diagram. We've got a box. We have 2 overlapping circles. This will be event A and event B. Perhaps we have 2 outcomes here, 1 outcome here, and 1, 2, 3, 4 outcomes here. So this symbolism comes from the idea of a union and an intersection. From last year, if you talked about the union of intervals that are increasing or decreasing, that was a U. And so that means union, I-O-N. Union means all. All the outcomes that are in A or B. So that's a total of 1, 2, 3, 4, 5, 6, 7. That's 7 outcomes. Now what we see in our formula up here is the intersection of A and B. So not a U, not the union, but an upside down one. That's called the intersection. Sometimes written as the word and. And what this means is the overlap. Where do A and B overlap? What outcomes are happening in both A and B? So an intersection, by definition in math, means what two items share, and they both share this one outcome. So that's just one outcome in the intersection. So the intersection of A and B means A and B both happening. So knowing that, we have this formula here, and our goal is to try to find a formula for this. So we have something equals something times something. And if I want to solve for this, then I'm going to end up getting rid of this times probability of A. I'm going to divide by the probability of A. And now all of a sudden I have a formula for that conditional probability. So dividing both sides by the probability of A gives us that the probability of B given A equals the probability of the intersection, so both of the things happening, over the probability of the given event happening. So this is the formula that we're going to end up using, and if you remember one thing about these notes, it should be this. So we're going to use this for the remainder of the examples. Example 1 says a bag contains 12 red M&Ms, 12 blue M&Ms, and 12 green M&Ms. That's a total of 36 M&Ms. What do you do with M&Ms? You take them out of the bag and you eat them. So this is something where we will not be replacing M&Ms. You're going to randomly choose 2 M&Ms. What is the probability that you choose a blue one on your second turn, given that you choose a blue one on your first turn? So some symbolism here would be the probability of a blue one on your second turn, so maybe B for blue and 2 for second, given, so our little bar from our formula, that you choose a blue one on your first turn, so maybe B for blue and then a 1 for the first turn. In the formula, I have the intersection, the probability of the intersection of both items happening, both events, so probability of blue on the second and blue on the first, over the probability of the given item, that second event that's here, so a blue on the first draw. So let's think about it. What is the probability of drawing a blue the first time around? Well, there's 36 total, and there's 12 blue, so that's going to be 12 over 36. Now, the probability of drawing a blue both times, well, the first time it's going to be 12 over 36, but then the second time, if you eat the first blue M&M, you now only have 11 to pick from that are blue out of 35 total. So if I do my multiplication straight across, I can get my fraction and I can simplify it. However, I notice that I have 2 numbers that are the same, one on top, one on bottom, and typically when that happens, we can cancel those out. So I end up with 11 out of 35. On number 2. Number 2's language is slightly different. It says in a school of 1,200 students, 250 are juniors, 150 students take art, 400 students are juniors who are also taking art. What is the probability that a randomly chosen student who is a junior is taking art? So this is what we want to know. But we need to reword it as find the probability of something given something else. So what is it that we know that is given? Is it given to us that the student takes art, or is it given to us that the student is a junior? The randomly chosen student who is a junior implies that we know that they are a junior. What we want the probability of is that they are taking art. So we're finding the probability that they're taking art given that they are a junior. So perhaps this looks like probability of A given J. I want you to pause your video and take a moment to fill in your formula here with the A's and the J's that represent art and junior. Pause your video. So check yours with mine, and let's find these probabilities. Let's start out with the simple one, which is the probability that the student is a junior. So there are 250 juniors in the school out of 1,200 students. So that's 250 over 1,200. On the top, we need the number of students who are both taking art and juniors, and that happens to be 40 students out of a total of 1,200. Now, I don't have two probabilities on top, and that's okay because we were given those values. I do need to divide my fractions, and when I divide fractions, it's the same as multiplying by the reciprocal. So I'm going to multiply by the reciprocal of this denominator, which is 1,200 over 250. I can recognize that 200 shows up on top and bottom, so those can be canceled out. I also can recognize that the 40 and the 250 are divisible by 10, so I'm going to divide those by 10, and I'm left with 4 out of 25. Number 3 says a fair 10-sided die was rolled. Fair just means that no side is weighted and all sides are equally likely to turn up. So a fair 10-sided die was rolled. Find the conditional probability that the number rolled was less than 5, given that the number rolled was even. So I want the probability of a number less than 5, that'll represent less than 5, given the number rolled was even. So filling in my formula, I want the probability that the number was less than 5 and even over the probability of something given, which was that it was even. So let's look at my sample space. It's a fair 10-sided die. So the sample space is all of the numbers from 1 to 10. So there are 10 possible outcomes. The probability that this is even, that I roll an even number, goes on the bottom. So the even numbers are 2, 4, 6, 8, and 10. That's 5 numbers out of 10 possible numbers. Now the top is a little bit trickier. I need the probability that I'm rolling a number less than 5 and even. So less than 5 means that I'm just looking at these numbers, not 5 or more, just less than 5. And it also needs to be even, and the only ones that are even and less than 5 are the 2 and the 4. So that's 2 out of 10. Now, just like before, I could do 2 over 10 times 10 over 5. That's going to allow the 10s to cancel out, and I'm going to be left with 2 over 5. Now, number 4 is a little tricky, simply because problems like this with boys and girls sometimes seem to be one way, but they are not necessarily that way. So it says your neighbor has 2 children. You learn that he has a son, Joe. That information is given. What is the probability that Joe's sibling is a brother? So of the siblings, we don't know if Joe is the firstborn or the secondborn. So either Joe is a boy and he has a boy sibling, or we've got Joe is a boy and he has an older female sibling, perhaps a girl and then a boy, or perhaps a girl and then a girl. So these are our options, either 2 boys, 2 girls, or a boy and a girl. They can be born in either order. But we don't know which one Joe is. We don't know if Joe is, if it's one of these, we don't know if he was born first or born second. So what is the probability that Joe's sibling is a brother? So we're trying to find the probability that Joe's sibling is a brother. So Joe is a brother and his sibling is a brother. So that's BB, boy, boy. And we're given that there is at least Joe. So there is at least one boy out of the siblings. So using my formula, I need the probability of boy, boy, and one boy over the probability that there is at least one boy. So let's do the denominator first. It's typically the easier one. The probability there is at least one boy. That happens 1, 2, 3 times. It doesn't happen this time. So that's 3 out of 4. The probability that there are 2 boys and at least one boy, well, that only happens when there are 2 boys. So that's 1 out of 4. So my 4s as my denominators will end up canceling out, and I'll be left with 1/3. And finally, our last type of problem asks us about environmental science students. Take a moment to try this problem on your own. Take a moment to check your work.